And get on the slideshow. Okay, everybody got that?
I'm seeing it.
Okay, good to go. Well, today is safety. A lot of this is just good stuff to know if you don't already. A lot of it doesn't apply necessarily to ham radio, amateur radio, but it's a lot of it is directly related to ham radio. So it's a mix, and some stuff is common sense, but it's all good to know. And there is one change, and we'll get to it in the thing that's coming up for all amateur radio operators this year as far as radio frequency exposure safety and assessments. Okay, let's move on here. Okay, this is in 3 elements. Each element has, I think, 12 questions. So we have a total of 36 questions that we'll go through today. And if you've been following along at home, we know that there'll be one question out of each segment that will be on your exam of 35 questions. So there'll be 3 questions out of the 36 that we look at today that'll be on the exam. And I'm not going to go a lot into electrical theory and things like that, but mainly just try to point out how you can make the selection if you've sort of forgotten or haven't gotten everything memorized. Some of the selections are pretty obvious. Some of them are a little more subtle. But the first section covers the electrical stuff primarily, batteries, wiring, fuses, and some of the hazards associated with those elements of the electrical side of amateur radio. So just going through the questions. First question, which of the following is a safety hazard of a 12-volt storage battery? The 12 volts, as you probably know or will know, pretty much all of our radios run on 12 volts DC, a power supply that you use to plug into the wall that will convert 120 down to 12 volts usually gives you about 13.8. But again, on the scheme of things, it's not a very high voltage shock-wise. The main problem is B, the correct answer, shorting the terminals can cause burns, fire, and explosion. Similar question, what hazard is caused by charging or discharging a battery too quickly? Here's one that if you have been around a while, if you look at the answer is overheating or outgassing. It can generate hydrogen gas, which if it's in an enclosed case, closed space, can be an explosion hazard. Now, the other 3 choices are, I'm not sure exactly what they are. They're sort of, I don't think they really refer to anything too real. It's sort of a combination, it's sort of like jargon. So overheating and outgassing is what you need to remember here about discharging or charging too quickly. In the United States, which circuit does the black wire insulation indicate in a 3-wire 120 volt cable? This is your normal house wiring in the US. House wiring is governed by both local codes and the National Electrical Code. And what you need to know is the black wire is the hot wire. If you've done any home wiring, you probably know this. Black is hot, white is neutral, and the ground is either green or bare copper. So hot, black. Where should a lightning arrestor be installed in a coax feed line? This is a problem we don't have too much. At least I'm in the Pacific Northwest, Bellingham, Washington, just south of the Canadian border. And the West Coast, we don't have a lot of lightning. And so it's not a big problem. We do have it though, so it's something you always need to keep in mind if you're setting up any kind of external antenna. The choices here are output connector or transceiver, access antenna feed point, AC power service panel. Basically, what you want to do is, if you're subject to lightning, is you want to make sure that any lightning strike, it's not going to get into your equipment. And so basically the correct answer is on a grounded panel near where feed lines enter the building. Got a little picture here. So this is, as I say, because there's such minimal, and I have such a small antenna at my home station, it's not really a factor here. There's the lightning's going to hit, if there is any, it's going to hit something much higher than my little antenna. But this is what it would look like if you've got a big external antenna and you've got feed lines coming in from outside into your house. What should be done to all external ground rods for earth connections? This is one you just have to know. I mean, some of these sound kind of reasonable. Waterproof them well. That's not really going to help. Keep them as far apart as possible. Now, you really want to get everything, essentially consolidate all your grounding if it's coming from, say, legs of a antenna or a tower or something like that. And the resonant frequency really doesn't apply to grounding. What's the purpose of a fuse in an electrical circuit? Again, this is just basic electricity, and you all know what a fuse is, or a circuit breaker, which is the alternative. And most houses now have circuit breakers rather than fuses, but if in your car, you'll have a fuse, a lot of fuses in your car, and the electrical system in the car. Basically, it's to remove the power in case there's an overload. In other words, you want the overload not to get to your equipment in whatever service it is. The A sounds like it could be right. You don't want to damage your equipment, but really just want to remove the power completely, which is, if you look at a fuse, you look at the little wire in a fuse, then when it's not connected, when it burns out, then that prevents any power from flowing through the circuit. So you want to remove the power in the case of an overload. This is a similar question. Why should a 5-amp fuse never be replaced with a 20-amp fuse? Now, if you've got something that in your equipment that doesn't want to see more than 5 amps, putting a 20-amp fuse isn't going to do any good as far as stopping the flow in a case of a overload, which is more than 5 amps, but less than 20 amps. And so it's not going to prevent the problem, and the problem is excessive current could cause a fire. In other words, if you had that 5-amp fuse, the fuse would have blown and you wouldn't have the problem. So you would have stopped the power, as we learned in the last question. Where should a fuse or a circuit breaker be installed in a 120-volt AC power line? This is one you have to sort of think about a little, but in series with the hot conductor. The hot conductor, that's where the power is flowing, the amperage is. And so you really want to stop that. And so that makes the most sense when you think about what you're trying to do with a circuit or a fuse, circuit breaker or a fuse. Parallel, as you know, if you've got parallel circuits, then it's going one way or the other. And if it doesn't go one way, it can go the other. So putting the circuit breaker in one of the parallel circuits isn't going to accomplish what you're trying to do. So hot conductor only in the circuit breaker. What health hazard is presented by electrical current flowing through the body? When we get into RF hazards, radio frequency hazards in the last section, and that's the one that you're going to learn most about in amateur radio and going to have to think about as far as things to prevent. The health hazard from a shock is all of these things can cause you a problem. Injury by heating tissue, disrupt the electrical functions of your cells, involuntary muscle contractions. If you, and most of you have probably gotten a shock at some point, and you can certainly have probably maybe experienced the C, involuntary muscle contraction. You know, as you're you jump back as you get shocked. But all three of these are things that can happen to the body as a result of electrical current. What's a good way to guard against electrical shock at your station? Again, this is common electrical practice or electrical information. 3-wire cords. You know, most cords these days have the grounding plug, the two blade plugs and the one round grounding plug, and all circuits are set up that way now for powered equipment. Having a common ground for all your equipment in the station. There's a lot of things you can, when you're setting up a station, there's a lot of good information in the ARRL manuals and things like that about how to properly ground your station. And then you can also, if you have a high voltage circuit, you can install mechanical interlocks. I'm not sure exactly how they work because it's not been a factor in my station. But all of these are correct ways to guard against electrical shock. And what hazard exists in a power supply immediately after turning it off? I think you may have had some questions on capacitors. Capacitors store the electricity and they store a charge, and if you let them alone, it'll dissipate over time. But if you touch something when they're still charged up, then you can get a shock off the capacitor. And so that's what you need to be careful of. And that's where your shock hazard occurs. And this is not to be confused with the flux capacitor, if you remember Back to the Future. Which of the following precautions should be taken when measuring If you recall a voltmeter, there's usually a number of, when you're measuring voltage, there's a number of scales. And so you sort of have to know what the range of voltage you're going to measure is, and then make sure you're on the right scale. Otherwise, if your scale goes up to 1 volt and you're measuring 120 volts, you're going to off scale the thing and probably break it. So that's why B is the correct answer. Ensure the voltage and the leads. In some cases, the leads may be pretty flimsy. If you get a free voltmeter from Harbor Freight, it may have pretty flimsy leads on it. And depending on what you're trying to measure, they may not be sufficient for the job. So make sure that your equipment matches what you're trying to measure. And that's the first section, mainly electrical stuff. Any questions on that before we go on to towers and antennas? Okay, towers are something, this is an element, there's a lot of questions you'll need to know the answer to for the exam, but in reality, probably more than 95% of you will never have to worry about tower safety, climbing a tower, grounding a 60-foot tower, things like that. And clearly, if all you use is a handheld radio, handy-talkie as we call them, you don't have to worry about grounding. And so a lot of this stuff is what you need to know if you're going to be involved in a tower. And you do need to know stuff about if you're going to put up an external antenna, what are the safety considerations there. But tower safety is something that you need to know for the exam, but unless you're getting involved with somebody else, or you do have the area, a location where you can put up a big antenna, if you're getting into, what we call DXing, distance communications with a lot of power and big antennas, then you need to know this stuff. Okay, so going ahead with B. Which of the following is good practice when installing ground wires on a tower for lightning protection? Well, we just went through the lightning protection thing, and we talked about grounding a little. Short and direct, again, mentioned that previously. So short and direct is the answer on grounding wires. And there'll be another question on this, which you'll already know the answer to. Again, you don't want to have right angle bends. You want to have them short and direct. Okay, this is sort of the common sense question. What is required when climbing an antenna tower? One, have sufficient training on safe tower climbing techniques. Use appropriate tie off to the tower in all times. Wear an approved climbing harness. These are all very logical and all very correct. You should not be doing any tower climbing without this sort of equipment and training. Again, another common sense. Under what circumstances is it safe to climb a tower without a helper or observer? Never. This is it's sort of should be pretty obvious. Another safety question on towers. Which of the following is an important safety precaution to observe when putting up an antenna tower? Again, the main thing, you want to steer clear of any overhead electrical lines. There's a lot of bad stuff that can happen if you get anywhere near the overhead electrical lines. The other things could be, well, you don't really want to get yourself grounded to your tower, certainly an A. So basically, if you're putting up an antenna or an antenna tower, you make sure you've got plenty of room for it. And this is a friend of mine. We hope he's got his antenna harness on. It's not clear. I know he had a safety line on there, but it's not for me. This is this is about a 60-foot antenna, I think 50 to 60 feet. And this is the problem you can have if over time you determine that you've got a bad connection up at there's an antenna rotor there, and maybe there's something wrong with the rotor. And so it's not an easy fix. And I would, if that was my tower, somebody else would be climbing that. I think he's in his mid-60s at the time of this picture was taken. Not recommended from my standpoint. Okay, what's the purpose of a safety wire through a turnbuckle used in tension guy lines? You saw the tension guy lines in that previous picture of the antenna. Secure the guy line if the turnbuckle breaks. Well, that's not likely. Wire is not going to be sufficient to serve as a substitute guy line. Prevent loosening of the turnbuckle from vibration. That's really the answer there. The other ones don't really apply. And I assume everybody knows what a turnbuckle is. Again, this is what you use to, once you think you know where you've got the tension on your guy lines, then twisting it one way tightens, twisting it the other way loosens it. And so you'll put a wire in there that'll prevent the thing from turning on its own and gradually loosening over time. Okay, a crank-up tower. Which of the following? I'll have a picture of the crank-up tower shortly here in the next slide. But which of the following is an important safety rule to remember when using a crank-up tower? Okay, painting and grounding doesn't make sense. Really, this is one where, we'll show you how the crank-up tower works if you're not familiar with one. But this type of tower must not be climbed unless it is retracted or mechanical safety locking devices have been installed. This is what a crank-up tower looks before it's been installed. It's so a telescoping tower where you've got, in this case, you've got 4 different sections. And if it's all the way cranked down, then and again, this is a pretty tall tower. You can see by the size of the step ladder next to it there. in a lot of small crank up towers, if you crank them all the way down, then you can get up on a step ladder, a regular step ladder, and attach your antenna. We've got some crank up towers, small crank up towers we use at our field day, and you can just get on a step ladder, put the antenna up, make all the connections, and then crank it up. And so you don't want to try to do stuff when it, particularly if you're climbing a tower like this, you don't want to crank it, go up. If it's extended, unless you're sure there are safety locks that will prevent it from suddenly telescoping down. What's the proper grounding method for a tower? We talked about grounding already. In this case, we'll just skip down to the correct answer is 8-foot ground rods for each tower leg bonded and connected to each other. What you'll get, a standard ground rod is an 8-foot copper rod, basically, that you pound into the ground. And so in this case, you'll want each triangular base tower, you want something on each of the legs. And then you want all those 3 ground rods connected. So you've got the tower connected solidly to 3 ground rods. Which of the following is true when installing grounding conductors used for lightning protection? Okay, we already know the answer to this. We don't want any sharp bends, so sharp bends must be avoided. And we know that common grounds is good, so that's not the right answer. We don't want right angles, and it doesn't really matter as far as the insulated wire. You want a good solid, mainly copper wire for your ground. So sharp bends to be avoided. Which of the following establishes grounding requirements for an amateur radio tower or antenna? Again, this is, as I said earlier, a lot of all the electrical stuff pretty much is governed by both national and local electrical codes. So whatever the codes are in your county or your location, your city, that's what's going to determine what you need to do as far as grounding. The FCC, FAA, these things, Underwriters Laboratory don't really apply. And what is the minimum safe distance from a power line to allow when installing an antenna? So we already determined from the answer to one of the earlier questions, we don't want to go anywhere near a power line if we can avoid it. And if we are anywhere near a power line, what we want to do is make sure that if the antenna falls down for any reason, it doesn't come any closer than 10 feet to the power wires. So you want to make sure you've got a significant margin of error. And so the other answers here don't really apply. And why should you avoid attaching an antenna to a utility pole? Well, we've talked about how dangerous it is getting your antenna to in proximity or touching a high voltage line, which you would have on a utility pole. You could have it on a utility pole, so that's sort of a no-brainer. The antenna could contact high voltage power lines, so that's why you don't want to do that. And that's element B. Any questions on that? Okay, now we get into the other type of hazard. We talked about electrical hazards with the shocks, with high voltage, discharging capacitors, that sort of thing. Now we'll get into what we call the RF, and this is the radiation. Before we get into this question, actually, the FCC and the rules regarding RF hazards are mainly concerned with the heating effect of a radio frequency radiation. And you can understand why when you think about what happens in a microwave oven. You put something in there, radiate it with the microwaves, and it heats up. The same thing happens to your body. If you're in close proximity to a radio antenna that's cranking out a lot of power, And so that's what you want to avoid. And all these measurements and concerns are related to that risk. And in the case here, an RF burn to your skin. So it's the heating effects of radio frequency radiation that we're concerned about, and pretty much this whole section here. The one thing that is changing this year is there are new requirements that the FCC is putting in place that become effective on May 3rd this year that require you to do basically a hazard assessment of the radiation that your equipment is putting out. And we'll get to that in just a bit here. But basically, it's the heating effects of radio frequency radiation that we're concerned about. And again, this is a sort of a sign you might see. Contact with internal RF source may cause burns and or electrical shock. How can you make sure your station stays in compliance with RF safety regulations? And this is the area I mentioned is changing this year. By reevaluating your station whenever an item in the transmitter or antenna system is changed. That's the correct answer. Again, we'll talk about the actual, what you need to do going forward here. So there's a new FCC requirement, and what it's requiring, this is sort of separate from the exam, but just something to know when you get your license, that this is a new requirement that's coming into effect. What you had to do previously, I guess previously, I'm not entirely up on all the history, but the FCC has always had RF exposure requirements for commercial transmitters, you know, the big radio stations and that sort of thing. But ham radio was exempted in the past. They're not exempted now, and so effective May 3rd this year, you'll have to do an assessment. Now, it's not as onerous as it might sound. This is an excerpt from the ARRL, the American Radio Relay League website. So you can do it, there's an exposure calculator. You can go in there and calculate what the exposure is, and it'll tell you if you're in the right ballpark. In other words, you need to know the power at the antenna, what sort of a duty cycle, and we'll talk about duty cycle in a little bit. It sort of gives you an indicator here of how to calculate it. For example, 5 minutes, transmit for 5 minutes and receive for 10 minutes. So that's like a 1 out of 3 that your duty cycle would be. And then your antenna gain, which is you can figure out depending on which antenna you got and what frequencies you're operating at. So this will tell you whether you're in the right ballpark or whether you're likely to create a hazard. Okay, back on the RF radiation. How does RF radiation differ from ionizing radiation, radioactivity? RF radiation does not have sufficient energy to cause chemical changes or in cells or damage DNA. Again, this is the difference between radioactive damage and RF radiation damage. Again, we've talked about the RF radiation is a heating up we're worrying about. Just think about your microwave oven. And this also, if you read this question, you understand this question, then you'll get the answer to the next one. What type of radiation are radio signals? Well, we just saw in the previous one that ionizing radiation was radioactivity, and so it's not gamma or alpha radiation, so it must be non-ionizing radiation. And here's the spectrum. So where we talked about microwaves, and you can see microwaves, what you heat your food up with and your coffee, is just above the radio frequency spectrum where the ham radio will be operating, and just there's an overlap about 5G. There are some 5G, the part of the 5G spectrum which you hear about these days with cell phones, the 5G cell phones, gets into the microwaves. And so if you were cranking out a lot of power on 5G, you can see you getting close to your microwave sort of area, which start heating up your hand or whatever. So again, and then the ionizing, where you get up into X-rays and gamma rays, the radiation concerns with the nuclear power and that sort of thing. Okay, this is one you just have to know. There's a chart which I'll show you in a second here. At which of the following frequencies does maximum permissible exposure have the lowest value? Okay, so frequencies. Now, I'll tell you that the chart is not in frequencies, it's in wavelengths. So how do you figure out what the wavelength is? You should remember that from somewhere previously. Wavelengths are the magic 300. 300 over 50 megahertz is 6 meters. And this is the chart. This should be in your books. And this is one you just have to remember. The other one we saw was 440, 3.5 megahertz, 440 megahertz, and 1269. 440 is just outside this band here. 70 centimeters is 440. So it's in the 50 meters. These are the 4 bands that are in the lowest exposure. In other words, you have to have the lowest power to get into the right exposure range. And 6 meters is the answer, which is 50 megahertz. So that 300, dividing 300 by whatever you're trying to convert is something that comes up a lot. What factors affect the RF exposure of people near an amateur radio antenna? We've talked about, you saw these elements, most of these in that little input for the radiation calculator. Frequency and power level of the RF field, distance from the antenna, and the radiation pattern. I can't remember whether you've had the antenna portion of the class yet, but there are, if you have, then you know there are different patterns depending on the type of antenna. A Yagi antenna has a different radiation pattern than a vertical or horizontal long wire, and so that the radiation pattern will also depend on it. So the answer is all of these can affect the radiation exposure, RF exposure. Why do exposure limits vary with frequency? Well, this is one you sort of have to know. It's just that the human body absorbs more RF energy at some frequencies rather than others. And that's what we've shown here, is that these are determined by how much it's exposed, it affects the human body. So all of these are correct. I mean, this one, D, is correct. Okay, which is the following is an acceptable method to determine whether your station complies with FCC RF exposure regulations? Again, this is relevant to the current requirement. You can calculate it based on an FCC bulletin. There's also a book that was mentioned at a presentation I heard yesterday. It's something like RF exposure in you, which has a series of tables where you can look up based on your particular situation. Calculation based on your computer modeling, that's one we just saw the input form for. And you can also measure the field strength using calibrated equipment. From what I understand, well, you will get an answer. Trying to do C by an amateur is not recommended because it takes very expensive equipment and very experienced operator to get a good answer. Now, all of these are correct, but what you'll probably do when you do, and my understanding is all you have to do is do the calculation, make a record of it, but nobody from the FCC is going to come knock on your door and say, okay, are you in compliance? The other thing to keep in mind, particularly as far as the safety is, it depends on where your antenna is. In other words, if your antenna is in your backyard, you've got a high fence around it, you just have to make sure your family knows what the RF hazards are in your area with the antenna. If it's out in your front yard and anybody can walk by and be exposed, then you've got a different thing. So you have to be more concerned about something like that. That's just something to keep in mind when you do get your license and think about putting up an antenna. Which of the following actions can reduce RF exposure to RF radiation? Well, this is again pretty sort of intuitive. You think about if you're standing next to a bonfire and all of a sudden it gets hotter, people are throwing more wood on it. What do? You move farther away from it. That's the same effect here. You locate the antenna in an area where it's not going to be accessible or less accessible, and so that'll reduce the exposure. Relocating the transmitter doesn't do anything because your transmitter is generally going to be inside your house in something like this, and so it doesn't really matter where you put the antenna inside the house. And increasing the duty cycle is going in the wrong direction. We'll talk about duty cycle in some of the remaining slides. Who's responsible for ensuring that no person is exposed to RF energy above the FCC exposure limits? This is a case where if, in the case that somebody was exposed and files a complaint, the FCC is going to come after you, the station licensee. So you're responsible for making sure that your arrangements, your station setup, your antenna is compliant with the regulations. And so it's your responsibility. Okay, now we'll get into the duty cycle a little bit. How does the allowable power density for RF safety change if the duty cycle changes from 100% to 50%? Now, 100% duty cycle means the antenna, the transceiver is on all the time. So you're transmitting RF energy 100% of the time. If you reduce that to 50% of the time, then it's the inverse. The power factor that increases the factor by 2. That says you can be half as close because it affects the average exposure. In other words, what you're doing is looking at over an average period of time, how much are you transmitting? How much are you pushing the push to talk? For example, in a normal net, if you're on a net, you may be on the radio for an hour and be talking for 2 minutes if you're just checking in. So you've got a pretty low factor there. And the average, it brings your average down. So it affects the average exposure. It doesn't, these other ones really don't apply. Just think about percentage of the time you're on the air, which is creating the potential RF hazard. What is the definition of a duty cycle during the average time for RF exposure? Well, we just talked about this, the percentage of time that a transmitter is transmitting. As I said, if you're on the air for an hour and you're transmitting for 6 minutes, then it's 10%. And that's it. Any questions? These are, again, pretty straightforward. Most of them are a lot of them are intuitive if you've done any electrical work. As I say, the one that is topical is the exposure limits, because this is a new change in the FCC rules that everybody needs to be aware of, certainly from May 3rd of this year. That's it. Let me get onto my screen share.